joining us. I'm really happy to see everybody here. My name is Megan Murray. I'm going to help facilitate this session and moderate some of the Q&A. We're joined today by Michel Perron, industry expert, mechanical engineer with over 35 years of experience in building energy auditing, building energy modeling, existing building commissioning, and he's actually been working with heat pumps and optimization since 1991. Michel, I'm going to hand it off to you to take us through the session today.
Thank you very much, Megan. Good morning, everybody. So today we're going to be talking about energy efficient and cost-effective heat pump operations for commercial building. The way we're going to proceed, the agenda for the morning, is we'll start with some fundamentals. I understand that probably many of you are familiar with heat pumps, but just so that we set the same basis for everyone, I'm going to go through some of the very fundamentals of heat pumps. Then we're going to go to the different type of heat pumps that you could have in your buildings. Either you already have those or you're planning in the future to have those. So we'll see the different options. And also the constraints, limitations on, like I said, operating efficiently. And when I say efficiently, it's both energy and cost. You'll see that it's obviously two things that can be quite different when you use a heat pump, especially when you have a dual source type of system where you have your heat pump and obviously you sometimes have a supplemental source of heating. We're going to end with some maintenance questions or maintenance items that you really need to keep on top of if you have heat pumps to maintain the performance of the system. And at the very end, obviously, we'll have 10 minutes of Q&A if there's any questions. But Megan, if there's any questions during the webinar, obviously you can tell me at any time, and I'll be happy to answer questions as they come along. So
Thanks.
Excuse me. Let's go with some of the heat pump fundamentals. Most of you are familiar with heat pumps. It's the vapor compression cycle. So you basically take heat at a low temperature and bring it to a higher temperature. Obviously, to do that, you use a compressor, which basically is the pump in the heat pump. It really is what will pump the heat from the cold outside air, for example, and bring it to your building as warm air to heat the building. So just to illustrate that visually, again, I know you are all familiar with that, but just to make sure we talk the same language here. This is the vapor compression cycle. This applies to your heat pump. This would apply to a certain extent to your chiller, to your refrigerator, anything that does air conditioning, or almost everything that does air conditioning nowadays, use the vapor compression cycle. So you've got your compressor, you have some form of heat rejection, which is the condenser, you have some form of expansion device. Here we have a very standard what we call DX, direct expansion device, and you have your evaporator, which can produce chilled water, which can produce cold air depending of the type of system. And to be very clear, we're going to talk about the efficiency of the heat pump, and that's called the COP. We're going to see that, and it's greater than 1. So sometimes people will say, well, the heat pump has an efficiency of 300%. Obviously, it's not really an efficiency. It's a way of illustrating the efficiency because it does not create energy. At 300%, you would say, hey, it's creating energy. It's not. So the way it works is you got your compressor, which actually will compress a hot gas. That hot gas will make its way to the condenser. So you got a really hot gas. It goes to your condenser. In the condenser, it will condense, obviously, into a hot liquid. That hot liquid goes through that expansion device right here. So you got your expansion device. So you got hot liquid at high pressure, goes through a small hole, and it will obviously expand, and it will reduce its pressure and reduce its temperature. That's where you get the cooling effect. So if it's an air conditioner, that part would be inside the house or inside the building. And if it's a heat pump, it's this part that's inside the building. So when you have a heat pump, basically if it's an air source heat pump, to take a very easy example, all you need is a 4-way valve to reverse the way the refrigerant flows so that in the winter, the indoor coil, if you have a furnace, it's an A coil, the indoor coil becomes a heating coil, and in the summer it becomes a cooling coil just by reversing the refrigerant flow. And obviously, this refrigerant that is now a cold liquid, which with a bit of vapor in it, will get evaporated by the air outside if it's an air source heat pump. So let's say it's -20 outside, you actually have to bring that cold refrigerant to a temperature that is colder than the outside air so that it can actually capture some of the heat from that cold outside air to evaporate the refrigerant, which then finds its way back to the compressor and the cycle starts again. So that's the same principle for anything that's refrigeration driven, that's compressor driven, using the vapor compression cycle. So the reason we say that a heat pump has an efficiency greater than 1 is because it will capture some heat from the source right here from, let's say, outside air. It's going to absorb, let's say, 1 ton of heat. The compressor will provide some energy to compress it, so that will add to that energy, and it will release some of that heat, all of that heat, into the building. So if you got the equivalent of 3.6 kilowatt of heat capture outside, your compressor will use 1.2 kilowatt if the COP is 3, so it's 1/3 of that, and it will reject 4.8 kilowatt into the space. So there's no energy created, it's just the compressor allows you to move heat from one source to another source, from a cold source to a hot sink through the compressor. So, and that's why you actually have 2 COP. When you're looking at your heat pump, most of the time people will provide you the COP in cooling. They say, hey, this unit has a COP of 3. That's usually in cooling. But as you saw in the previous slide, the COP in heating will always be higher because it includes the compressor power. So this COP of 3 is the cooling COP. You also have a COP in heating, which would be 4 in this case. So a heat pump, regardless of the type of heat pump you have, will have 2 COPs, 1 in cooling, 1 in heating. The one in heating should be higher than the one in cooling because the useful heat, which is right here, QH, includes the compressor work, whereas it does not in cooling. So now we know what heat pumps are, and there's different form of heat pumps. We'll see the different types that can be applied in your buildings when you want to improve its efficiency, move towards decarbonization. So that's one thing, the type of heat pumps. But then you have to look at your rates, because when you put the heat pumps, yes, you want to decarbonize, but you also don't want to really increase your energy cost significantly. You want to be able to manage that cost. And the structure of your energy rate is very important. And for the Ontario commercial customer, you have 2 class of customer. And I'm not saying class because there's one is lower class and a higher class, but you've got class A and class B. And I'm not talking the type of buildings, really the size of buildings. So the class A customers are usually on the commercial side above 1,000 kilowatt of peak demand, average peak demand in the summer. And the class B will be lower than that. And they will pay a different type of rate, a rate structure. You need to really be aware of your rate structure when you start dealing with heat pumps, because you will likely need supplemental heating, and then you can manage your cost by properly using that supplemental heating, as we'll see. So typically you'll pay something in the order of about $12 to $15 per kilowatt, sometimes per kVA, for your peak demand. And you will pay then an energy cost. If you're a class B, it will be in the range of about 10 to 14 cents. So you do pay what's called a global adjustment based on the kilowatt hour basis, not on a kilowatt basis. And there's a base charge. So you'll end up around that. It does vary because the global adjustment charge will vary month to month. So let's say it's about 12 cents total per kilowatt hour. Sometimes can be 14, sometimes can be 9. Remember, though, you need to know what is your marginal cost of energy when you start evaluating your heat pump, because you need to always treat the demand aspect of the heat pump and the energy aspect separately. And you always pay the energy of a heat pump at the marginal cost of your electricity. So 10, 14 cents for a Class B. A Class A, that's where it can make a big difference. You pay your global adjustment on a kilowatt basis, coincident with the 5 peak hours in the year, which are currently mostly in the summer, but your energy cost will be much lower. It's usually based, I mean, and again, there's variation between clients if they have the different type of contract they have, but if you pay on the hourly energy price, you may be in the 2 to 6 cents range. So your energy cost can be really low and your demand cost can be quite high. So if you've got a heat pump, you can run that heat pump as long as you're not on peak at a really, really low cost. And the heat pump is quite efficient. We said it can have a COP of 4, sometimes it can have a COP higher, sometimes lower, but you actually pay quite a low cost. So a lot of Class A customers, if they have the ability to use a heat pump, they could actually financially benefit it. Instead of seeing an increase in their electric cost, they could see in their total energy cost, I'm going to correct myself, they could see a reduction. Whereas for a Class B customer, because the kilowatt hour is higher, you have to be very agile in how you're going to implement the heat pump in order to maintain your cost at the same level it is now if you don't have heat pumps. So again, summary, remember you need to know the incremental price of your energy, because that's why you need to apply to your heat pump consumption, and you need to know obviously very well your demand cost, and is the heat pump going to be on peak demand, because then you're going to incur a demand cost. So I'm located in Quebec, and I can tell you that in Quebec, heat pumps have been used for like 50 years in a hybrid type setup because of our demand charge. Our demand charge is quite high. Our energy cost is quite low, so people will use heat pumps, but they will always manage the peak demand by using some form of supplemental heating that typically will not be electric in order to make that heat pump the most economical. And obviously, it's still very, very efficient. So that's about the rates. So your rate structure is important. And I will again mention, do not ever use the blended rate when you do your heat pump analysis. If you want to know, is a heat pump good for my building? Stay away from a blended rate, which is the average rate you would pay on a yearly basis, because that has no meaning when evaluating a heat pump. So that's really the basic rule. There's a quick example here. It's not as drastic as sometimes it's way worse than this, but in this example, if you replace a 20-ton heat pump gas-fired rooftop unit with a 20-ton heat pump unit replacing a gas-fired unit, you can see the difference if you use a blended rate compared to the energy rate and the demand rate. So in case of a Class B customer, you can get 35%, 15% difference between the actual cost and the one with the proper approach. And for a Class B, the error can be 35%. So you have to be very careful. Otherwise, you can make errors that can be significant in your decision on moving from a gas-fired system to a heat pump system. And I've seen in Class A, sometimes the error can be more than 50% because of the difference between the blended rate and the actual marginal energy rate. Your blended rate can be 16 cents and your marginal energy rate could be 5 cents. So the error can be really, really more significant. This is actually an example that shows you a fairly mild difference, even though there still is a difference that could be significant in your decision to move to a heat pump. So that's the one thing that's really important about heat pumps. You're likely going to have a dual energy source if you really want to manage your peak. We'll see that there are some heat pumps where you don't need that, and you need to use the proper rate. Now, the type of heat pumps. We're going to go through the different type of heat pumps that you are more likely to consider in your building. The one that I see the most often around our ways too, and I've seen some of those in Ontario because I do work a lot in Ontario. So we'll start with one that you may say, this is not a heat pump, but it is. We saw the vapor compression cycle, and I told you a chiller is basically the same thing as what we saw. It has all those components. It's just that compressor can be different, the expansion device can be different, but it still works as a vapor compression system. So heat recovery chillers, they used to be removed way back in the 90s. People, I remember working in large building downtown Toronto, and they had heat recovery chillers, and they actually, when the chiller was due to be replaced, they never put a heat recovery chillers back because they were slightly less efficient than a conventional chiller. But the heat recovery chiller is a very valid concept for large buildings that, and sometimes medium-sized building that have hydronic heating, hydronic cooling, especially when you have a low temperature loop. I've just audited a large building in Toronto where they actually are going back to a heat recovery chiller in order to recover all of the heat from the building. And instead of throwing it outside through a cooling tower, they actually are now using it to heat the building. There are two types of heat recovery chillers. There's the conventional that we call double bundle chiller. Those are the more efficient type of heat recovery chiller. Like the name says, you've got two condenser bundles. One is called the standard condenser, and one is the heat recovery condenser. This heat recovery condenser, which is that second bundle, will allow you to obtain higher temperature water out of the condenser. So that will allow you to inject heat that could go all the way up to maybe 130 degrees Fahrenheit. I have it in Celsius in the next slide. I'm an old guy, so I work a lot in Fahrenheit. And you also can retrofit an existing chiller that's not a heat recovery chiller by using a plate heat exchanger coming out of the condenser to recover the heat before it goes to the cooling tower. The drawback of this configuration, even though it's easier to retrofit and it's cheaper to retrofit, is that the temperature level of your recovered heat is much lower. So you really need to have a low temperature loop in order to take advantage of this type of heat recovery. So very good measure to put in a commercial building that has chillers, that has hydronic heating, that's not necessarily high temperature. Now, the one thing you also have to be very careful when you start using heat recovery chillers. The one thing you have to stop doing is free cooling. When I said that you want to use your heat recovery chiller to provide heat to your building and you stop throwing heat outside, always remember a cooling tower, an air side economizer, those systems, what they do is reject heat outside your building. When you use free cooling, you are basically throwing heat outside the building that could be used to heat the building. So when you have a heat recovery chiller, you have to stop using free cooling for all the systems that are connected to that chiller because you want to load up the chiller, even in the winter, with the highest possible cooling load. So you recover all the heat coming back from your return air, cool it with your heat recovery chiller, and re-inject it. So obviously it's something that requires quite a bit of a change in culture in the way the operating team would run the systems. Now, the heat recovery chiller is one very convenient system that is used, that used to be used extensively in large commercial buildings, but the drawback is even with the double bundle chiller, you sometimes don't have enough temperature to be able to meet your load because you're limited to fairly low temperature. So if you have a reheat loop, very often the heat recovery chiller will be used to inject heat in a reheat loop because it's a low temperature loop. If you got a loop dedicated to your air side coils, the heating coil, that's also a low temperature loop. But the perimeter heating in a building is usually a high temperature loop that wants water that's between 140 and 180 degrees Fahrenheit. And the heat recovery chiller cannot do that job. So then you have to go to more complex system I've seen a few of those. They're not very common yet. It's a cascade heat pump. So you'll have your standard chiller. So you got your standard chiller that's right here. And on the condenser of the standard chiller, you put a heat pump that will take the heat out of that condenser, will basically boost it to a temperature that can go up to about 160 degrees Fahrenheit. And then it can be used in a lot of perimeter hydronic heating loops. So it opens the door to more application, but it's obviously more expensive because now you not only do you have your main chiller, but you have to have another which smaller heat pump that will boost that condenser water temperature to a level that can be used in your building. So there's an additional cost, and there's also an additional penalty in terms of energy performance because now you have two COPs to deal with. You've got the COP of your chiller, and then you have the COP of the heat pump on top of that. So you do lose a bit in terms of efficiency. But it's still more efficient than an electric boiler or a gas-fired boiler, obviously, but it's less efficient than if you had a single-stage type of heat pump. So like it says here, this type of application provide you with a higher range of temperature. So that's the really one large benefit of it. You can go from 60 degrees Celsius to 80 degrees Celsius range. You will have that penalty in terms of COP. And it's obviously higher cost. So you've got the pros and the cons that are shown in every slide. And in this case, like I said, if you want to move towards a heat pump, you've got a large chiller, you've got a hydronic heating distribution system. The cascade system is an option you can consider. Now, if you don't want to go to a water source type system, say, okay, I'm moving away from the chillers. I want a central air source hydronic heat pump. So instead of using basically the building heat, the internal gain to provide you your heating, because that's what the first two systems we saw, their source is your internal gain. The internal gain is what heats your return air, which basically is what is used for the chiller because they cool the return air before it goes back to the building. So if you move away from that, and now I'm not using my internal source as my heat source, you will use the outside air as your heat source, just like a residential heat pump. But you do have commercial type of system that will be able to do that kind of work, and it's air to water. So you've got an air to water heat pump where you will install that unit. This is the exterior unit, and it will be used solely for the purpose of heating the building. Even though we called it heat pump, it will be used typically as a source of heating. The limitation you have with this system is the fact that it uses the outside air as its heat source. So when it gets really cold outside, you get two impacts. The capacity of that system will drop with outside air, and its efficiency will drop with outside air. So it will be limited in how much energy it can provide you. If you try to size a system to provide 100% of the load of your building using an air source, central air source hydronic heat pump, you would pay quite a bit because the last 20% of the capacity would be used for very few hours in a year. So it is always better to have a hybrid system if you go with an hydronic air source heat pump. Now there's a table here that shows you what is the impact of the temperature on the system. So when you go to minus 20 degrees Celsius, you see that the hot water delivery temperature is only 27 degrees. So very few buildings can heat with water that would be that cool. So again, you can heat the building with 60 degrees water when it's 8 degrees, but as it drops, you can't. So you'll have to either have larger perimeter rads, which means very expensive retrofit, or you have to have low temperature loop, or you will have to actually cascade that again with another heat pump that will boost that water temperature that's 60 degrees to a higher temperature. So Used straight, as we saw, it has temperature limitation. So that's also a rule that you have to keep in mind before you start thinking of heat pumps. We talked about the rates when we're looking at the different type of heat pumps. Always remember, what is the temperature level? Heat pump is not about energy. A heat pump can provide a lot of energy. The problem is the temperature level that you will need. So you need to know your loop requirement. Sometimes you can reconfigure a loop. You can have loops that can be split because some of it distribute to your perimeter heating, and maybe the same loop goes to a glycol heat exchanger to provide hot glycol to your makeup air unit. Well, a makeup air unit does not need a lot of temperature because you can heat to 18 degrees Celsius with water that would be at 30 degrees Celsius. So you don't need 60 degrees Celsius for a makeup air unit on the glycol loop. So you may do some minor repiping, sometimes it's not that minor, where you can split loop so that now you have a low temperature loop, and now you can use that type of heat pump. The air source heat pump that we saw will be sufficient to provide heat for that loop. So you really have to start looking at how can I manage the temperature levels of my different loop in my building. And if you can segregate those, split them apart, then you open the door to using a heat pump more effectively. So the pros and the cons for the air source heat pump: the retrofit is actually not too difficult to do. You will add that outside air unit. It will be applicable to a wider range of buildings compared to just the chillers, because the chillers are usually in larger building. They're not as much in a mid-sized building. Obviously, when you have that source, that type of heat pump, you will not be able to provide both heating and cooling at the same time. Whereas the heat recovery chiller will always provide both cooling and heating. You will always be able to cool your air coming into your building through your air handling unit with your heat recovery chiller. The air source heat pump can do just one job at a time, and it is limited in the temperature at about 60 degrees. There are models that can provide somewhat higher temperature, but you pay a really high penalty on the COP as you go higher in temperature. So the 60 degrees is not a technical upper limit. It's more of a practical upper limit because of the electric cost that comes with a reduction in your COP. So air source heat pump can be applied on a hydronic system. Now we're moving to one of the more efficient, if not the most efficient type of heat pump. We all heard about central ground source heat pump. And I do insist I'm talking here about a central ground source heat pump, because we're going to talk about another type of ground source heat pump in the next slide. So the central ground source heat pump can be designed without supplemental heating. That is the one source of heat pump that may be designed where you will not need supplemental heating, where the system will provide you all of the heating required. So you don't have to worry then about, do I need still to have natural gas, or how am I going to provide for that supplemental heating? Is it going to be an electric boiler, in which case my demand might skyrocket and it would be not economical to have it? Well, the central ground source heat pump doesn't have that problem, because it takes its energy from the ground, which is not really impacted significantly by weather changes. So we'll have always, even if it gets really cold outside, you still have that same capacity. Obviously, the big drawback of that system is that for every ton of heating capacity, you will need, and that's a really approximate number, 150 feet of well. And those are usually closed loop vertical well. It's very rare nowadays that you see an open well system where they use the groundwater in a heat pump. It is possible, but because of the very often regulations attached to that, most of the systems are closed loop, where you'll have 500 feet deep well, which will be about 3 ton. And you'll need one. Obviously, you need to evaluate how many wells do I need. You will do a test well to make sure that the ground has proper characteristic for your ground source heat pump. So always have test wells, unless it's a really small system and they already know the characteristic of the ground around that system. So Very efficient. You will cut your heating cost by 3 in this case. You will likely cut your cooling cost by maybe 20%. They can be more efficient than a chiller, but it's very close because a chiller is a very, very efficient machine. The ground source is very efficient in cooling, but like I said, nowhere as efficient as it is in heating. So you can, if you want to do a rough estimate, take your heating, translate if it's in cubic meter of gas, translate that in kilowatt hour, obviously taking out the efficiency of the boiler. So take 80% of your cubic meter, put that in kilowatt hour, and then divided by 3. That will give you how much kilowatt hour you will need to run a ground source heat pump. So the difference with the total kilowatt hour would be your savings. So very efficient system, but quite expensive. And you need a lot of ground because you need to dig those wells, unless you go with an open well system. And like I said, those have their own constraint and difficulties in implementing. But by far the most efficient, just as a rule of thumb, a ground source heat pump system in a commercial building will cost between $5,000 and $10,000 per ton to install. So it can be quite, and it can be more depending on the availability of ground. If you have to really, take apart a parking garage to put the ground source heat pump, it can be even more expensive. And the ground source heat pump I just mentioned is central. So you got one big central heat pump equivalent to a chiller that will distribute that heat throughout the building or cooling. So it does one job at a time. In the winter, it provides heating. In the summer, it provides cooling. You can have the same configuration of ground source heat pump using distributed heat pumps. Distributed heat pumps are fairly common. A lot of mid-size buildings in Ontario use distributed heat pump in their building. So you will have heat pumps in the ceiling space very often throughout the building. They're usually connected to a loop that has a boiler and a fluid cooler or cooling tower. The boiler will inject some heat in the winter, and the fluid cooler will reject the heat in the summer. Now, if you take out the boiler and you take out the cooling tower, you can convert that system to ground source, because now instead of using the boiler and the cooling tower, you use the ground to take some heat in the winter and reject the heat in the summer. So the distributed heat pump system combined with a ground loop is the most efficient. It's more efficient than the one that we saw before, which is a central heat pump, because now you get each of those heat pump in the building. They can be one in cooling if it's in the center, and one in heating if it's the perimeter, and the heat from the one in the center that is being rejected in the loop can be used by the perimeter unit to heat the space. So they recover the heat within the building and only go to the ground when it's needed. So it's even more efficient than the central heat pump system. Now, if you already have this type of system and say, hey, I only need to replace my boiler and my cooling tower, which is, I say only, that's still a big undertaking. I replace those with a ground well. I'm going to dig, 50 wells, and I'm going to connect my system. And now I just converted my existing hot water distributed heat pump system to a ground source system. This is not going to work because the heat pump that you have in the building, in your ceiling space, are different model. When you have a ground source heat pump system on a distributed loop, the heat pumps are extended, what they call extended range. They need to be able to work with a loop that goes as cold as 0 degrees Celsius. Actually, usually it's a 4 degrees Celsius. So this heat pump has to be able to have really cold water in the winter, whereas your standard heat pump loop that's designed with a boiler has not an extended range. It needs water in that loop that's probably no colder than about 64 to 68 degrees in the Fahrenheit. I'm sorry about the Celsius and Fahrenheit. Fahrenheit in the winter. So be careful. You have the piping structure to be able to convert that system to a ground source heat pump, but the heat pumps themselves are unlikely to be able to work with a ground loop. But again, very efficient system if it's designed as a ground source heat pump. Even without the ground source heat pump, the one thing you can do with this system, you can replace the boiler with an air source heat pump. And now that air source heat pump can provide the heat in the winter. You may need a small electric backup, but it will become an air source heat pump type of distributed water loop. So you replace your natural gas boiler with an air source heat pump like we saw before, and boom, you have converted, you have decarbonized your loop. The only thing is, because it's an air source heat pump, in the coldest days, you might need a little boost from either a gas boiler or an electric boiler if you really want to fully decarbonize. The other type of distributed heat pump that you will sometimes see is what we call the VRF system, a variable refrigerant flow system. Sometimes they're called VRV, but you'll see them. The one brand name that's often seen is called City Multi. There's a whole other, there's a whole other family from different manufacturers. Those are very similar to distributed heat pumps. So you have what they call heads all over the building, and those heads, they provide you either cooling or heating. If it's a system that's called a three-pipe system, some of the units are in cooling, and the units that are in cooling, they reject heat into the refrigerant through an intermediate line, and that refrigerant that's been rejected, so it's rejected heat from the units that are in cooling, can be used by the units that are in heating. So you can recover the internal heat of your building to provide, for example, to the perimeter zone, and the system will recover the heat. So it's very efficient. You also have a model of this system which does not have this third line that allows heat recovery, and it becomes a big heat pump. So the units are all in heating in the winter and all in cooling in the summer, and the outside unit becomes the equivalent of your heat pump evaporator in the winter and a heat pump condenser in the summer. So that would be a VRF unit. The drawback of a VRF unit is that you have a lot of refrigerant. You've got refrigerant line running all over your building and a lot of refrigerant. So as the line of refrigerant gets longer, the COP of the system drops. Some people ignore that fact, but as you extend the distribution network of those VRF systems, you can get a significant penalty in your COP, because if you think about it, the compressor, which is outside in this unit, becomes the pump. And as you have longer line, that compressor has to overcome all the resistance of sending that refrigerant further and further. So it's a little item that sometimes gets dropped in the conversation when you want to retrofit your building to a VRF system. So we have the pros and the cons for that type of application. A VRF system, by the way, the pros is really, it's a fairly easy retrofit. You don't pass water lines, it's just small refrigerant line. It does not do a whole building, but you can add multiple VRF. There's times where the VRF units are connected to a water loop to connect all of those exterior units together, if I can say. So there's a lot of configurations that are possible. The water loop heat pump is a very efficient system. The drawback is the difficulty that you would have in retrofitting that system because of the cost involved if you want to go with extended range heat pump for a ground source system. The easier conversion would be to replace that boiler with an air source heat pump. That would allow you to do quite a bit of decarbonization without doing a major retrofit to your entire loop. The last type of heat pump or I think it's the last type of heat pump I want to cover here, is the air-to-air rooftop unit. So you've got your typical rooftop units, gas-fired, very few are electrically heated. Nowadays, you can find a lot of hybrid or just purely heat pump rooftop units. Enbridge actually has, or I think still has, an incentive for the hybrid heat pump units. So those systems is basically just an air source heat pump with a gas-fired supplemental heat in most cases. The one thing I would say about this type of unit is make sure if you have a BAS that your unit is BACnet compliant, because you want to be able to control when the supplemental gas comes in, because you want to be able to control your peak demand. So you always follow your building peak demand. And if you see that your peak is going to go above a certain level that you will establish, that is your, let's say, economic sweet spot, you want to be able to command that unit to switch from heat pump to natural gas. Otherwise, you will be at the mercy of the OEM controller, which will not know your building demand. It will switch based on temperature, and that may not be the economic sweet spot for your building. So air source heat pumps in rooftop units are very good when they're hybrid. If you connect them to your BAS, if you have a BAS, it's obviously even better. And they are limited in outside air temperature under which they can work in heat pump mode. Typically, at about -15, they will switch over regardless of your peak of your building. Below that, you can keep them working, but their COP really drops and their capacity really drops. So you will not have sufficient heating capacity. Again, it's often a capacity issue that will catch up to you when you go too low with the heat pumps. A quick word on mini split. Obviously, for smaller building or sometimes for just a section of a building, you can put mini split. Mini split can be extremely efficient. There's probably the one type of unit in air source heat pumps that are the most efficient. If you buy a cold climate heat pump, it can work to -30 degrees Celsius or -25 depending on the model, and maintain good capacity and very good COPs. So mini split units for small retrofit of specific spaces can be very efficient. Try to select one that can go down to -25, so a cold climate heat pump. Like I said, it will maintain its efficiency. The drawback with a lot of mini split is that you cannot integrate them into your BAS. They're really difficult to integrate, so they become standalone controls, which because of their size is not too big of an issue, but if you got a lot of those, it can become an issue because you don't want to have multiple controls all over the place. Last word on the heat pump, very, very quickly. If you start into the heat pump conversion world, you can look at if you've got an electric tank or a small gas-fired domestic hot water heater. Those are fairly easily converted to heat pumps. There's two types of heat pumps, by the way, for domestic hot water. The most common one is the one you see on the screen. It's a heat pump that uses the inside air as a source. So it's basically an air conditioner that you're running, let's say in your mechanical room. So it cools the mechanical room and use that heat to heat the water. But if you put that in a small cupboard, the cupboard's going to get really, really cold, and it's not going to provide enough heat, and the backup electric element in there are going to kick on, and you're not going to get a lot of benefit out of this. It will become mostly an electric tank rather than a heat pump tank. So that's the one type which has the condenser evaporator inside the conditioned space. The other one is a split system. We don't see them very much yet, but you will have, basically it's an air source heat pump. You have the evaporator outside and the condenser in the water heater. It will need a backup element, it always does. Its efficiency will be lower in the winter because it works with outside air as a heat source, but it will not air condition the inside of your mechanical room or the cupboard. So that's the big difference between the two. Now, efficient operation, I think throughout my discussion this morning, I talked about it. So some of the golden rules to really operate your heat pumps properly and to have them run as efficiently as possible is know your temperature requirements. Your heat pumps will have definite range in which they can work efficiently. So you need to be able to apply the heat pump that will best fit your temperature level. For heat recovery chillers, avoid free cooling. You want to increase your cooling load. It's sometimes counterintuitive, but that is definitely something you need to do. Always try to reduce the temperature lift. One of the first slides we saw was a slide where you had the outside condenser evaporator, you had a compressor, and then you had the condenser inside. That's the temperature lift or the pressure lift. For a heat pump to be very efficient, you want that lift, that pressure differential between condenser and evaporator to be as low as possible. And that has a lot to do with proper maintenance. So you want to make sure your heat exchangers and your coils are well maintained. It is more important than if you've got a gas boiler, because the gas boiler can provide heat at 180, and even if you're going to 185, it's not going to have a major impact. It will have some impact, but it's fairly minor on the efficiency. For a heat pump, the impact is much more important. So maintenance of the coils to reduce that lift is really important. Last thing is, when you do a setback, right now you've got your building, you reduce the temperature at 18 degrees at night, and it works fine. A heat pump has lower capacity than your standard boiler. So it will take longer to reach the temperature that you want in the daytime. And more importantly, if you're asking the heat pump to provide too much capacity too fast, it will revert to the supplemental heating. So your setback can actually cost you, because instead of coming back doing your warm-up with the heat pump, you may end up doing your warm-up with supplemental heating if your controls are not set up properly. So always be careful with setback. The way it's done around here is very often the setback is modulated when you have heat pump with the outside air temperature. As it gets colder, the setback is not as deep to allow the heat pump to recover without having to go to the supplemental heating. I talked about integration with the building automation system. You do not want your heat pumps to be this isolated island that works on its own, even for rooftop units. If at all possible, obviously, if you have a BAS, you want something that is BACnet compliant, so you can connect to that heat pump and you can control when it's going to work and when it's going to go to, let's say, natural gas backup or any other backup to properly manage your demand, because that's where the heat pump can get you, is if you don't manage the demand properly. With VRF, we talked about VRF, they can be a bit difficult to integrate. The newer model of VRF are BACnet compliant, or some of them are BACnet compliant. Some of them require what we call a gateway, which is a translator between protocol. So make sure if you go the route of VRF to install in your building to decarbonize, that it can be integrated into your BAS. Otherwise, you will have controls issue on the long run, I can guarantee you. And same thing, I think we mentioned that supplemental heating. You want to be able to control that, and you will manage, and I'll show you with the next slide, when you have heat pumps that require supplemental heat, and we saw anything that's air source basically requires supplemental heat. You will usually combine it with another source of heating, usually natural gas, sometimes, but rarely electric. So what you want to do is you want to have on your BAS a live measurement of your building demand. This is a must-have. You should not install a heat pump of any significant size that has supplemental heat without tracking your demand, because now you can manage that demand usually on a monthly basis, because your peak demand is charged on a monthly basis. And I'm disregarding GA right now, but if GA was in play in the winter, you would also manage based on GA. And you will really turn off the heat pump when you see that your peak demand has reached a preset maximum. And usually that's based on an economic calculation. And I'll show you an example. If you've got hourly values, if you have hourly electrical values, which usually can be obtained in almost all LDCs will provide you your electric hourly or 15-minute demand profile. If you have hourly gas data, what you can do is really you plot the electric profile of your building and you plot your gas profile. And what you want to do when you install your heat pump, you want to fill in all the valleys, because then all you pay is the marginal rate of electricity, because you're not creating any demand. So By looking at that through a spreadsheet, you can actually get a really good estimate. How much can I take out of my gas by filling the valley without creating a peak? And it will both tell you the size of the heat pump that you need to do that, the amount of cubic meter that you will be able to transfer from your boiler to your heat pump, and it will tell you how much kilowatt hour will be required by that heat pump. So by having those profiles, you can answer a lot of your questions, and that applies regardless of the technology that you're using. Rooftop, then can be a central air source heat pump, can be a heat recovery chiller. By having that information, you can actually calculate the impact of optimal management of your heating system, of your hybrid system. Because right here, you see I've got a flat line. I did not create a new peak, so I know all of my electrical energy for the heat pump is at the marginal rate of energy. And you see in this example, I did the calculation for a specific building and we had $45,000 cost reduction or $46,000 cost reduction by going to a hybrid heat pump system. Whereas for a Class B, because of the higher marginal rate, the best we could achieve with a properly controlled hybrid system was an increase in cost of $148,000. It's not always going to be an increase, but for a Class B, it will often be an increase. But at least with this approach of using your profile, you can look what is the impact, and there's no guesswork involved. There's not any assumptions other than the COP of the system involved in this. So, but do you require to have hourly gas data? There's techniques where you can take your monthly data and distribute the monthly gas data on an hourly basis based on heating degree days, but that becomes an estimation. Last word before we go to the Q&A is about maintenance. Told you maintenance is critical for heat pump because your efficiency is really proportional to that delta, the pressure differential between the condenser and the evaporator. So you want to make sure it is maintained properly. You need to check your refrigerant level. You need to make sure that it is at the proper level, that your coils are correct. You want to reduce, and I'm not reading the slide, you'll have those slides. There's more here. You want to make sure that you don't lose too much air through your ductwork because, again, the capacity of heat pumps is more limited than what you're used to. So you want to minimize any kind of losses. Obviously, you'll have to clean the coils, which you would always do. The condensate drains have to be obviously cleaned probably more than once a year. So there's a bunch of maintenance consideration that should be included based on the type of heat pump you select in order to maintain that efficiency. As I said, maintenance has a much larger impact on the performance of heat pumps than it would have on boilers or even chillers. So you got to make sure that this item is not left as a second thought once you installed a heat pump. It should be part of a good training program that you give your operating team if you go down the road of using heat pumps. And Megan, I said I was going to leave 10 minutes for Q&A. I left 7 minutes. So sorry if I went a little fast somewhere there, but I know I had a time constraint here. So if there's any questions, I'm be happy to try to answer any of the questions you have.
Thanks, Michel. I learned a lot going through that. It was a lot of information in a very short amount of time, but especially the cascade systems, I've been reading about that and not fully understanding them, and the way that you explained it really helped me out. We got one question about incentives. So you mentioned Enbridge incentives for hybrid heat pumps, and we can respond to that question. I also want to mention the Save on Energy retrofit program also offers some incentives for heat pumps. You get incentives on the electricity savings that the heat pump might provide. So they might be smaller than what you expect, but you're able to combine as well with Enbridge's incentive program. I personally recommend just contacting one of Enbridge's energy solutions advisors, they're called, and they will help you with your application.
All right.
Okay. I'm just gonna that background noise. If anybody does have any questions, we're really open to hearing. I like discussing the questions. Even if you have feedback about our session today, we would love to hear that too. Juan, you can unmute yourself and ask your question. Even turn on your camera if you like.
Yeah. Hello, good morning. Thank you very
Morning.
much for the class. Was awesome. I have one question regarding the heat pump water heaters. Is there a significant different price difference between the both options that you described before?
Yeah, the package unit, the one that you can just drop in, is quite a bit cheaper. So just to give you an idea, if you go for an electric tank, let's say you got your standard 60-gallon electric tank, will cost you, if you buy it, $500 to $600. The equivalent heat pump will be about $2,500, maybe between 2,000 and 25. That's the package unit. Now you go to an exterior unit, you will double that price again because you have to install that exterior package, pass the line. So the installation cost is significantly higher because it requires this external installation. The one benefit of the split system is that you can get larger capacity. So if you say, okay, my typical office building does not require a lot of domestic heat, you can get away with the equivalent of a 60-gallon tank or a 100-gallon tank, which you can easily get as a package unit. If you have a high demand, so you're in a pool or an arena where there's locker rooms, you should actually use a heat recovery elsewhere, but you probably would go to a higher capacity system, and those will be split units. So really it becomes a choice that's imposed on you. When you get to larger system, you're going to go very often to split units.
Okay, thank you very much.
You're welcome.
Thank you. Okay, we've got about 4 minutes left. So if you want to just take us through the next couple of slides, Michelle, I'm going to share some resources with our audience. We do offer some virtual one-on-one coaching if anybody would like some access to some of our energy experts that we work with here. There's a post-webinar support form. We also have a monthly bulletin. You can sign up for news and information about resources and events that we're going to be hosting. Our live training calendar is always up to date with future sessions that we've planned. And the Save on Energy training and support webpage is linked here as well. You can access that on saveonenergy.ca. And some of our previous recordings are there, as well as resources that we create. I'm just seeing one more question pop up.
I had changed the slide on you without you telling me.
That's okay. That's okay. This slide is actually a promotion for the Energy Management Awards for this year. There are still some spots to register. That event is happening on the 29th of October at the International Center in Mississauga. I hope to see some people there. One last question. Have you ever studied the installation of heat pumps in greenhouses?
Yes, actually, a couple of times because Hydro-Québec has done a couple of projects, pilot projects with heat pumps in greenhouses. Unfortunately, they did not have the most outstanding results. One of the reasons for that is that a lot of the heating system used in greenhouses were also there to provide CO2 for the plants. We call funny enough, in French, I don't know in English, they call those dragons. So they use actually those dragon in greenhouses to heat the greenhouse and at the same time provide some of the CO2. When they went to the heat pump, they went to ground source heat pump because they did not want the supplemental heat, but then they had to provide a liquid CO2 tank to provide CO2 to the greenhouse, which became added to the cost of the whole system. So that was the drawback they had, at least in the couple of case studies or pilot project that they did in Quebec with heat pumps in greenhouses. Obviously, the capacity is really large, so the cost was really large also because of the very high capacity required for greenhouses.
Interesting. Did you notice any impact to the crop itself?
No, the crop itself, that other than the fact that they obviously realized that for the type of crops that they had to provide CO2 on an external means. The size of the unit were large enough. The ground source loop was so large that they did not have a problem with capacity. It became a question of economics. It was just not financially viable because of the size of the ground loop that was required to maintain the proper conditions in the greenhouse.
All right, well, that takes us to the end of our session today. I want to thank everybody for being here. There's one last slide just about some more Save on Energy resources. You can sign up for Save on Energy's quarterly business newsletter. There are some links to the social media pages and our email address if you need to reach us. So thank you all. Somebody also asked about sharing the PowerPoint. Yes, we will share a PDF version of that, and they'll also be posted to the Save on Energy webpage.
Thank you,
Thanks
everyone.
very much.
Thank you, Megan.
Thank you, Michelle.